All right, we're going to take a quick look at function transformations. Now, to start off with, we need some basic definitions that you should already have. This should already be in your notes from earlier in the year, which is what's a parent function, which is the thing that's going to be transformed. So in order to work with that, you need to know that the input of the function, what's going in the parentheses in function notation, those are your x values. And the output of the function, what you're getting out at the end of the function, those are going to be graphed as y values of a function. All right. Now, before you get to this point, you should have already done our exploration in class. And if you haven't, you can follow the link and do that now. All right, so the first transformation we looked at were shifts. These are equivalent to what we saw as translations in geometry class. They're moves of your function to the left, to the right, up or down. All right, so a shift of h units to the right will look just like this, f of x minus h. And a shift of k units up will look just like this, f of x plus k. So it's just sort of a preview of what those two things will look like. All right, so here we have our parent function. This is a parabola, it's a quadratic function. So right now you see both, but as I move this, and I'm just gonna quickly emphasize these lines. All right, as I move the blue line, you can see I'm increasing the value of h. Right now h is 3, and you can see that it's 1, 2, 3 units to the right of where it started. And if I make h a negative number, for example, -3, that means it's f of x minus -3, or f of x plus 3, and that represents a shift of 3 units to the left. So it's something you should be aware of, that when you're working with left and right shifts, it is sort of counterintuitive. You get shifts to the right represented by x minus the number of units to the right, and shifts to the left being f of x plus the number of units being shifted to the left. Overall, though, this is the form for a shift of h units to the right. And along with that, here again is our parent function. And if we have the form f of x plus k, in other words, we're taking our y value, f of x is our y value, and adding k to it. So as we increase k, so again, let's say 3, that represents a shift of 1, 2, 3 units up. So right now I'm focusing on the vertex, but at any place you look, here, for example, it's 1, 2, 3 units up. Here it's 1, 2, 3 units up. Everywhere where your points were in your original function, every point has been moved 3 units up. So it's your y value, f of x, plus 3. And similarly, if we were to move it down from the parent function, this is where k is -4. That would be f of x plus -4, or f of x minus 4. So that's a shift of 4 units down. All right, so we have our parent function, and then we can shift it left or right, up and down. And we can, of course, combine both of those. We've also looked at stretches. All right, so this is the basic format for a stretch. A times f of x takes each original y value and multiplies it by a. And taking a look at what this will look like. Here again is our original parent function, where a is 1. Because if you're multiplying something by 1, it's not being changed. Now, if we go and increase a, notice as you increase a, you might describe the graph as getting skinnier, and that's one way of looking at it. Values greater than 1 will make skinnier and skinnier parabolas, if that's how we're working with it. But we can also see that we're at whatever value we're at, we're 3 times more. So at the vertex, or the vertex is 0 here, well, 0 times 3 is still 0, so it doesn't change. The vertex is still in the same place. But this location, let's see if that'll show up. Maybe not. This location, where y is 1 on our parent function, you can see that the value of the function, the y value, at that point right up there, is 3. And similarly on the other side of the axis of symmetry on this parabola. And any other values you pick, so 2 on the original parent function, you could guess what it should be on our shifted function. You should be able to work it out already. If this is a value of 4, then that same place on our parent function is going to be 4 times 3, or 12. And this works no matter what. So if we make a fraction, if we make it between 0 and 1, like it is right here, again, remember the red function is our original function. Notice that at each point, the value of the function is half of what it was before. So here, the value of the function of our original function is 1. On our shifted function, it's 1/2. Here, our original function, the value at this point, the y value, which is always what we're talking about when we're talking about value, is 4. And in our shifted function, it's 2. Half of 4 is 2. Now this also leads to something else, which is what happens when a is negative. And the same thing happens, so fractions lead to these wider functions. And again, we sometimes think of fractional values as making wider functions. And it's still the case, but we also notice that it's now upside down. So the rules still work. Values greater than, rather more negative than -1 will make skinnier functions. Fractions, values between -1 and 0 will make wider functions. But if it's just -1, you notice it's the same, just flipped. It's the same amount wide, just flipped. And that's our last real relevant rule here, which is that we can reflect a function across the x-axis by putting a negative sign in front of it, effectively. That will flip our function. I should add there are a few additional rules, but they're just not as relevant to our study right now, as we will really be focusing on parabolas for the most part.